Hello students, today we're going to be working with bisectors. There's two types that we're going to be looking at. The first is perpendicular bisectors and the other one is angle bisectors. So please make sure you're taking notes as you go, and if you need to, ask the teacher to hit pause in order for you to get some notes written down. So the first thing I want to make sure we know is what bisectors are. We've talked about two of them already, just kind of want to remind you what they are. But a perpendicular bisector is either a line, a ray, or a line segment that's perpendicular to a line segment and goes through the midpoint. That means it's going to cut exactly into two pieces. The angle bisector can also be a line, array, or a line segment, and it bisects an angle through its midpoint so the two angles formed are congruent. So perpendicular bisector causes two pieces to be congruent, and angle bisector causes two angles to be congruent. They're going to be the exact same measures. So we have two theorems that are associated with the perpendicular bisectors. The first one here is if there's a point that's on the perpendicular bisector on a segment, then it's going to be equidistant from the endpoints of the segment. So what that means is I have some point P anywhere on this line. If I were to connect point P to the endpoints here, so either to A or to B, then those two lengths are going to be exactly the same length. And similarly, if a point is equidistant from the endpoints of a segment, so this is the converse, then it's on the perpendicular bisector. So in this case here, I'm telling you there's a point P somewhere, and the distance from P to A and P to B are exactly the same, but that means if I were to draw a perpendicular line, it's going to be the perpendicular bisector, so it's going to cut exactly into two pieces here. So similarly, we have two properties with angle bisectors. Remember when we did before, the shortest distance from a point to a line is the length of that perpendicular to the other line. So just keep that in mind. That's what we were doing with last unit when we found the distance from a point to a line. So for our angle bisector, if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. So it's kind of similar to the perpendicular bisector. We have ourselves an angle bisector there, so it cuts this into two congruent angles. And our shortest distance is a perpendicular distance. That's why there's right angles here. And what it's saying is if there's a point here, if I were to find that shortest distance from the point to the line, that those two distances are going to be exactly the same. And the reverse is also true. If we have a point somewhere within the angle, it's equidistant from our sides, again we're using the perpendicular distances here, then what that means is that that's going to be on the angle bisector. So again, the perpendicular bisectors and the angle bisectors have very similar theorems to each other. So let's do an example with this. I want to know what is the length of AB, so this guy here. So what I can see from this is that BD is a perpendicular bisector. And the way that I know that is that not only is it going from point B and perpendicular to the opposite side, but I'm cutting this exactly into two congruent pieces. So the first thing I know is that segment BD is the perpendicular bisector, which means the length of AB is equal to the length of BC. That was the first theorem that we just went through. So now I'm going to set up an algebra equation. I'm going to say that 4x is equal to 6x minus 10 because those represents the lengths AB and CB. And I'm just going to use algebra to solve. So I'll subtract 6 from both sides, and then I get negative 2, and I'll divide negative 10 by negative 2 to get the value of x is equal to 5. Now, my actual problem want to know what is AB, so I'm going to have to substitute that back in. I'll do 4 times 5, and that'll give me 20. For our next example, this is now using an angle bisector, same exact idea. If I have an angle bisector, that means these two lengths here are going to be exactly the same as long as we have those perpendicular lines there. So Rn is an angle bisector, that means MR is equal to RP. So once again, we're going to set up an algebraic equation. I'm going to set 7x equal to the 2x plus 25, and I'm going to solve. So I'm going to subtract 2x from both sides, getting me 5x, and then I'm going to divide. In this case, I coincidentally also get x is equal to 5. But once again, I want to know what the length is of Rm, so I'm going to substitute that value back in. So for this one, Rm is equal to 7 times x, or 7 times 5, which is 35. Now, just like with the medians and the altitudes and all that fun stuff, we also have concurrency of perpendicular bisectors. So in this case, the point of concurrency is called the circumcenter of the triangle. If I left that little part out, please make sure you write that at least somewhere underneath that theorem so that you know what the term is called. I believe I did leave that on the notes, and I apologize for that. So please make sure you're writing down the fact that the point of concurrency for perpendicular bisectors is called the circumcenter of the triangle. So what this theorem is saying is the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. So what I mean by that, if I were to create all the perpendicular bisectors, they're going to all meet at one point. Now these are different from the altitudes. Altitudes go from a point and is perpendicular to the opposite side. And it's also different from a median because a median just cuts this into two congruent pieces but also goes to the vertex here. These are not going from the vertex. These are just the perpendicular bisectors of each side, and they're meeting at a point. And what this theorem is saying is that if I were to find the distance from that point to each of these vertices here, that you would see that they're exactly the same. What I wanted you to kind of see with this circle over here is if I were to draw that triangle inside a circle, you would see that point P here should be exactly in the middle, which means these are all radii, so they're going to end up being the same. So that's why it's called the circumcenter, because it's as if there's a circle around it and it's the center of that circle, so on and so forth. So we actually have three cases for this. We can have an acute triangle in which our circumcenter will be found inside the triangle. We can have a right triangle where once again it's going to be on the right triangle, or we can have an obtuse triangle in which the circumcenter ends up outside of the triangle. So keep that in mind. Just like the altitudes, there's three different cases. With our perpendicular bisectors, there's also three cases, either inside, on, or outside the triangle, again depending upon what kind of triangle that we have. So here's an example of how we're going to be finding the circumcenter. We're actually going to be able to figure that out. So in this problem, I'm giving you 3 points. P is at 0, 6, O is at 0, 0, and S is at 4, 0. So there's two things, just like we need only two altitudes to find the orthocenter, we only need two lines to find ourselves the circumcenter. So the first thing we want to do, now this is a right triangle, so it's going to kind of be a little bit easier for us. What we want to do first is choose one of the sides, and we're going to find the midpoint of that side. So say I chose PO as my side, I'm going to find the midpoint. So since it's here at 0, 0 and 0, 6, the midpoint is found here at 0, 3. So since this is a straight up and down line, our perpendicular bisector is going to be a horizontal line. Then from there, we're going to then find the midpoint of the line down here, OS, because once again, the ones that go straight up and down left to right are going to be the easiest for us to work with. So what we're going to do here is going to find the midpoint once again, and then draw a perpendicular line. If instead we had done a line that was slanted like this, what you're going to need to do is first find the midpoint of that line. So for example, this would actually be the midpoint of that line. And then you need to find a perpendicular line. So you'll need to find what the slope of this is. You'll find the slope is down 3 and over 2. So a perpendicular line would be a positive 2 over 3. And you can draw the line that way. The last thing you're going to have to do is after you draw your lines, you're going to need to find where the perpendicular bisectors intersect. And it's at this specific point here where x is 2 and y is 3. So the point of intersection is at 2, 3. So that means the circumcenter is at 2, 3. Now the angle bisectors also meet at a point of concurrency, and this kind of sounds a little bit similar to a converse of what we were just doing with the perpendicular bisectors. But the idea here is that the bisectors of the angles of a triangle are concurrent at this point P, and what happens is it's going to be equidistant from the sides of the triangle. So this is now talking about the sides of the triangle, while the perpendicular bisectors said that the distance from the vertices are going to be the same. So specifically here we've got PX is going to be congruent to PY, which is also congruent to PZ. So those three lengths are going to be exactly the same. So for this one here, it's going to be called the incenter of the triangle. So once again, if that's not written down, I believe it's not on there as well. Please make sure you're writing that somewhere, that where your angle bisectors meet, it's called the incenter of the triangle. And this is, if we were to draw a circle inside our triangle, you would see that from that point where they all met up, that they would be equal distance to where we're hitting here. It would be the same thing because they're all the radii as well. So just to do one more example, in this problem here we're going to be finding the incenter and we're going to be using it. I'm telling you the length of GE is represented by the expression 2x minus 7, and that GF is represented by the expression x plus 4, and what we want to do is actually find the length of GD. So what we know is that G is the incenter because that's the point of concurrency of our angle bisectors, and by the theorem that we just discussed, the distances from the incenter to the sides of the triangle are equal. So what that means is GD here is equal to length here of GE which is equal to the length here of GF. And do you see how this is not necessarily a perpendicular bisector? It can end up being that way, but do you see how this length is significantly longer to this length here? It does not have to be a perpendicular bisector, just perpendicular distance to the line. So what we're going to use the idea here is that GE is 2x minus 7 and GF is x plus 4. Since they are equal, we're going to set up an equation that set them equal to each other. So 2x minus 7 is equal to x plus 4, and then we're going to start solving this as an equation. Decide how you want to move things around. I'm going to start by moving the 7 to the right hand side to get 11, and then I'm going to move the x over, and I end up with x is equal to 11. So I'm going to subtract the x from both sides. So now I can find one of the two lengths, GF or GE. That's going to be the exact same thing as what GD is. So if I find, say, GF, I know my equation is represented by x plus 4. So I'm going to take the value of 11 and add 4 to it to get 15. And since I know that GD and GF are the exact same thing, that means GD is equal to 15. The teacher will now hand out to you a piece of paper for you to work on. You may write on that piece of paper, do as much of the work as you can, and when you are done at the end of the period, please turn in what you have completed. If you want to take it home, you may take it home and work on it and bring it back tomorrow and turn in the beginning of class. The more practice, the better, but we are going to continue practicing once we get into class tomorrow. Again, I'm sorry I'm not there today, but I will see you tomorrow. Have a great day.